Welcome. Today I'd like to talk to you about lines and curves in space. And so to start out, I just want to draw a three-dimensional coordinate axis. So we've got our x-axis, we have our y-axis, and we have our z-axis. And then what I'd like to do is, let's say that we have some line passing through space. So I'll just draw this line. Okay, so this is a line, let's call it L. Okay, and let's say that I know a point that is on this line. I'm going to call that point P sub 0. And then let's say I also knew a vector that was parallel to that line. So let's say there's this little vector out here, and I'm going to call this the vector V. And V is parallel to L. Then I can do the following. If I have a point P0, and let's say that this is X, Y, Z, and on the line L, then we can say that some other point on L, so let's say I drew another point on here, let's call this point P, then that point P is equal to P sub 0 plus T times the vector V. All right, so some multiple of V. So in other words, if I put V on here, stuck the vector V on the line, and then multiplied it by some constant, I would get to P. And that does make sense. And so one way of thinking about this is the following. That if I want that point, xi plus yj plus zk, then that's going to equal to my initial point P0, which I'll write as x0 times I plus y0 times j plus z0 times k plus t times v. But v is v1i plus v2j plus v3k. All right, so this would be a way of writing this new point. Now, another way of saying this is that I have a function of t, I'll call it r, and that function of t is my initial point, r sub 0, plus t times the vector V. Okay, so that's just a similar way of thinking about it. Okay, another way that I could write this, and I think that this is the most helpful, is to write this as a parametric equation where t is called the parameter of the function. So let me rewrite this. I could write that x, or the x value of some point on that line, is going to be x sub 0 plus t times v sub 1. Y is going to be y sub 0 plus t times v2, and z is going to be z sub 0 plus t times v sub 3. And notice that if I write this in parametric form, so I have an equation for x, I have an equation for y, I have an equation for z, but each of them are in terms of this fourth variable t, then what goes right here, you can see me circling this x0, y0, z0, that's the point that I know that is on the line. In other words, that's my p0. And then over here I have v1, v2, v3, and that is my vector v. So that's how I can set up a parametric equation for a line in 3 dimensions. Okay, let me write this down real quick. The equations are called the standard parametric equations of the line through the point P0 parallel to vector V. Okay, so those are called standard parametric equations, and right here are my 3 standard parametric equations for that line. Okay, so let's do an example of this so you can kind of see how this works. So, quick example. Let's find parametric equations for the line through the point -1, 1, 2, parallel to the vector v, which is equal to 2i plus j plus k. All right, so what I have here is I have an initial point, P0, and I have a vector v that is parallel to the line that I want. So I can set up parametric equations here, x, y, and z. And this initial point P0 up here, this guy, I just plug in the x0 value, -1, right here. I plug in 1 right here. I plug in 2 right here. So that's the initial point of this line, plus t times v sub 1. Well, v sub 1 in this case is 2. So that's plus 2t, plus this is plus 1t, plus this is again plus 1t. So this would be a set of parametric equations for a line. Now, as you remember, like in 2 dimensions, lines are super simple, right? We remember like our point slope equation for a line or something like this. Well, in 3 dimensions, you just can't write a nice, clean equation for a line without using a parametric equation, at least not in general. So we need this extra variable t in order to write an equation for a line, and instead of it just being some simple equation like y equals mx plus b, we have this set of 3 parametric equations that describe a line in 3 dimensions. Okay, let's try one more of these. So, an example. Let's find parametric equations for the line through the point P, which is -1, 1, 1, and Q, which is 0, 3, 2. Okay, so I want a parametric equation for the line that passes through those 2 points. Now, what I know about is if I'm trying to find a parametric equation for a line, I need to know a point on that line. Well, I've got that. I actually have 2 points on the line, right? I have P and I have Q. I know both of those. And I need a vector that's parallel to the line. Okay, that I don't have, but I can get it because I can use these 2 points to give me a vector that is parallel. Okay, so what I'd like to see is, well, what's the standard form of the vector from P to Q? And I can say, oh, okay, well, that is, I'm going from P to Q, so I take 0 minus -1, 0 minus -1 times I, plus 3 minus 1 times J, plus 2 minus 1 times K. All right, so let's rewrite this. And I have that my vector going from P to Q is I plus 2J plus K. All right, so now I have a point. I could use either of these points, really. It doesn't matter. I think just for my purposes, let's use this second point, 0, 3, 2, as my point. So my point P0 in this case will be 0, 3, 2. And then I have a vector from P to Q. Let's use those two together to find my parametric equations. So I need an equation for x, an equation for y, and an equation for z. So the point goes in first. I put in 0, 3, and 2 from the point P0, plus, well, in the first one I get 1 times t, which is just a t. In the second one I get 2 times t, or 2t. And in the third I get 1 times t, which is just t. So if you don't like that 0 sitting there, I could rewrite that this is x equals t, y equals 3 plus 2t, and z is equal to 2 plus t. And that is a parametric equation for the line going through point P and Q. Very good. Okay, so let's do one more example that's a little more interesting. So a helicopter is to fly directly from the origin in the direction of 1, 1, 1 at the speed of 60 feet per second. So where is the helicopter at time, at time t is equal to 10 seconds. Okay, so what I'd like to do is I would like to create a parametric equation for the flight of this helicopter. Okay, so first of all, if I want to create a parametric equation for the flight of this helicopter, then I need to know a point which this helicopter flies through, and I need to know a vector. Well, fortunately, I actually know both of those things even right now. What I know is I have a point that this thing flies through, 0, 0, 0, and I know a vector because it goes in the direction of 1, 1, 1. So my vector v will be 1, 1, 1, or if you prefer, I plus j plus k. All right, so now what I'd like to do is I'd like to say, okay, but this vector, if I write out a parametric curve here, it may or may not be helpful. Okay, what I mean is, let's write out a parametric curve, x, y, and z. And what I'd put in is 0, 0, and 0, and then plus t, and plus t. Correct? So in other words, x equals t, y equals t, z equals t. But at a time of, let's say, 1, how far has this helicopter actually traveled? Well, it moves 60 feet per second, so it's moved 60 feet. If I plug in 1 right now, though, to my set of parametric equations, I get 1, 1, 1. At time 1, I'm not at 1, 1, 1. I'm 60 feet out. So this isn't quite right. And so what I need to do is I need to say, okay, when I've moved 1 unit in the t direction, it would be quite good if I had moved 60 feet in the v direction. And the way I'm going to do this is the following. First, I'm going to start out by, instead of looking at v, another vector that is very similar to v, and it points in the same direction. So I said that v is equal to I plus j, plus j plus k. Well, let's look at v divided by the magnitude of v, which is just a unit vector. Well, what's the magnitude of v? The magnitude of v is the square root of 1 squared plus 1 squared plus 1 squared. In other words, it's the square root of 3. So I'd like to divide the vector v by the square root of 3. If I did, I'd get 1 over root 3 I plus 1 over root 3 j plus 1 over root 3 k. All right, so here is a vector that is of unit 1. Now, I don't want the helicopter to move 1 each second. I want it to move 60 each second. So what I'm going to do is I'm going to do the following. My function, r of t, that I'm looking for, I want that to be whatever point I start at plus t times whatever speed it is that I want to travel times v over the magnitude of v, which is a unit vector. So now I'm saying move your speed, because remember this unit vector over here, v over magnitude of v, it just has length 1. So now this vector is going to have length my speed, which is exactly what I want. Okay, so let's fill in the blanks here. What I want is, so x, y, and z are going to be, well, R0 is just zeros. So 0, 0, and 0. And then I get plus t times speed. Well, what is my speed? Well, it's 60, and so I get 60 times my I component of my unit vector, which is times 1 over the square root of 3 times t, plus 60 times 1 over root 3 times t, plus 60 times 1 over root 3 times t. And so the question is, where will I be in 10 seconds? Okay? So where I'll be after 10 seconds is the following. So what would x, y, z be when t is equal to 10? Well, it's going to be 60 times 1 over square root 3 times 10, 60, 1 over root 3 times 10, and 60, 1 over root 3 times 10, which is, let's see, that's 600 over root 3. Is there a better way of saying that? I suppose that there is. So this is 600 over root 3, and this is 600 over root 3. So where will this thing be? I think if I simplified that down a little bit, so my point at which I'm going to be, x, y, z, after 10 seconds, I think that 600 over root 3 reduces to 200 times root 3, 200 times root 3, 200 times root 3, if I just rationalize that denominator. And so this is where my helicopter will be after exactly 10 seconds. So now I'd like to go over a few definitions. First definition, the points x, y, z, which are equal to, I guess you could call it f of t, g of t, h of t. You could think of each x, y, and z as a function of t, where t is in some interval I, make up the curve in space that we call the particle's path. Okay. Second thing, definition. The vector r of t, which is equal to the vector from the origin pointing to p, is f of t I plus g of t j plus h of t k from the origin to the particle's position is the particle's position vector. Okay, one last definition, and then I'll talk about this a little bit. We call r of t a vector function. Or a vector valued function. Okay, let me talk about this for just a second. Particularly this idea of a vector-valued function. So let's say that I have my axes. We have x, y, and z. And I have some curve in 3 dimensions, okay? So maybe, just for the sake of argument, let's say that it's some spiral shape like this. So what I mean by r of t is a vector that points from the origin to a specific point given a value of t. So maybe at t equals 0, the vector points here. At t equals 1, maybe the vector points here. At t equals 2, the vector points here. And as you raise the values of t, the vector keeps pointing at different places on this curve. And so it just kind of follows the spiral up. So a vector-valued function is a function of vectors in which each of those vectors point to a point on this curve in space. Okay, so there's kind of 2 ways you can think of these functions at the same time. One way is you can actually think of that as the spiral is the vector-valued function. Another way is you could think of it as a sequence of vectors pointing to the spiral. Both of those ways of thinking about vector-valued functions are correct, and sometimes it will be more useful to think of it one way than another way. Okay. Now, those are vector-valued functions. We call real-valued functions Now remember, the things that come out of vector-valued functions are vectors. If what comes out of a function is a real number, we call that a scalar function. So we call real-valued functions scalar functions, and that's important to remember. Okay, so let's take a quick look at an example. Let's graph the following vector-valued function. Let's say we have r of t is equal to cosine of is equal to cosine of t times I plus sine of t times j plus t times k. All right, and I'd like to graph that vector-valued function. So to do this, since we're not as familiar with these types of functions, let's just plug in some values for t and see what we get. So let's say that t was equal to 0. And maybe I'll just make a chart over here. T. And then what do I get in the x direction? What do I get in the y direction? And what do I get in the z direction? So if t is 0, then I plug in 0 for cosine of t to get my x direction value. This is x, y, z direction. So what would I get? Cosine of 0. Well, cosine of 0 is 1. Sine of 0 is 0. And 0 is 0. So I get the point 1, 0, 0. So I go 1 in the x direction, 0 in the y, 0 in the z, and I get this point. Okay? So now let's plug in another value for t. Let's say, just for fun, let's plug in pi over 4. Okay, so cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. And then, of course, I'd get pi over 4 for z. So I get square root 2 over 2. Out in the x direction. Square root 2 over 2 in the y direction. Puts me right here. And then I go up pi over 4. So I go up to this point. Okay, so now let's try pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And then I get pi over 2. So I go 0 in the x direction, 1 in the y direction, and then up pi over 2. So I kind of come up here. This is sort of hard to see. You kind of have to use your imagination a little bit. This first point is out 1 in the x direction. This third point I've done is out 0 in the x direction, but it's over 1 and up pi over 2. So it's kind of curling in. Okay, I could keep this up, and what I'm getting is a spiral shape. It's going to spiral up like this. And so you can kind of see how we can use this method to graph a curve in 3 dimensions. These are what we call vector valued functions, and you'll get a chance to look at some of that in your homework. Okay, so if vector value functions are indeed functions, then we should be able to use calculus on these functions. For example, we should be able to take, let's say, the limit of a vector valued function. Now, taking the limit of a vector value function is not very hard, because typically what we would want to do is we'd want to take the limit as t goes to some fixed point t0 of r of t, our vector valued function. And the way we're going to do that is we're just going to take the limit of each component individually. In other words, I'm going to take the limit as t goes to t sub 0 of f of t times I plus the limit as t goes to t0 of g of t times j plus the limit as t goes to t0 of h of t times k. And so I just take the limit of each component. So if you know how to take one limit, you really kind of know how to take the limit of a vector valued function, because you're just taking the limit 3 individual times. There's really nothing new going on here. So for example, let's do a quick example here. Let's find the limit as t goes to pi of r of t, where r of t is equal to sine of t I plus cosine of t j plus 3t times k. So what I'm going to do is I'm just going to take the limit as t goes to pi of r of t, I'm just going to take that limit of each of the components individually. Okay, so let me erase here, and I'll do that. So what I want to do, the limit as t goes to pi of r of t is just the same thing as the limit as t goes to pi of sine of t times I plus the limit as t goes to pi of cosine of t times j plus the limit as t goes to pi of 3t times k. And each of these limits is quite easy. The limit as t goes to pi of sine of t, this limit. Sine of pi is just 0. So I get 0i. Then if I plug in pi for cosine of pi is -1, so I get minus j. And then if I plug in pi to 3t, I get 3 pi, so I get plus 3 pi k. Or if you prefer, the limit is just going to be -j plus 3 pi k. And that is the limit of that vector valued function. So really there's nothing really new here. If you know Cal 1, you know how to take the limit of a vector valued function. You just take the limit individually of the I component, the j component, and the k component. And that's really all there is to it. Okay, the same can be said of vector value function continuity. So I just want to talk about that for 1 second before I let you go. So let's write a definition. So a vector function r of t is continuous at a point t is equal to t sub 0 in its domain if the limit as t goes to t0 of r of t is equal to r of t0. And really this is no different than the limit is no different than the definition of continuity at a point for real valued functions. Now we're just taking 3 limits instead of 1. So if the limit as t goes to t0 of r of t equals r of t0, then we say that this vector valued function is continuous at that point. Let me finish this up. The function is continuous if it is continuous at every point in its domain. Okay, so we can just take our knowledge of continuity from Cal 1, and if you don't really remember what continuity is from Calculus 1, it might be good to remember such things. That if we think about vector valued functions in terms of just like 3 separate I, j, and k real valued functions, then continuity is exactly the same. So all the things we know about continuity from Cal 1 now apply to Calculus 3 in terms of vector valued functions. So that's very nice. That's where I'm going to leave you. You now should be able to do some homework over parametric lines and curves in space. Good luck on your homework.